Hello students, welcome back to my YouTube channel. This is Kashima Soni and today we are going to start another topic of the series carboxylic acid derivatives that includes the chemical properties of esters only. So far we have discussed about alkaline hydrolysis and the evidences related to the same. So if you have not checked out any of the videos related to it, the link is mentioned in the description box. Check that first and then switch to this part of the video for better understanding. So without wasting any more time, let's just discuss the acidic hydrolysis in detail. Alright, so without wasting any more time, let's just switch to the mechanism of acidic hydrolysis. See, acid hydrolysis of ester, it is exactly same as that for your acid catalyzed esterification, because all the steps are reversible in either of these cases. Okay, so let's see what is exactly happening in the mechanism over here. This ester over here, you can see it is now getting protonated and with this H positive ion. So your ester is going to act as a nucleophile. Okay, it will get protonated over here. After protonation, you will get this particular protonated ester, and over here you can see your oxygen is carrying positive charge. Okay, so oxygen will try to retain its electronegativity by accepting a pair of electrons from this pi bond, making this particular carbon electrophilic, which makes it susceptible to get attacked by this water molecule present over here. Now, after this attack of water molecule, what is happening exactly? It leads to the formation of this particular structure like that. Okay, so over here you can see this oxygen again, it is carrying positive charge, and oxygen is actually electronegative in nature. So it will try to retain its electronegativity by accepting this the pair of electron from this particular sigma bond between OH, and now what is happening? Deprotonation is occurring in this case, which is giving you this particular structure. Okay, and now again what is happening? Protonation will occur and it leads to the formation of this particular structure like that. Now, what is happening? Your lone pair of electrons are back donated from your oxygen to this bond between carbon and oxygen, and this ROH will get released when your oxygen carrying positive charge will be accepting a pair of electron from this CO bond, and it will be releasing your alcohol R-OH from here, giving you this particular protonated carboxylic acid, which after deprotonation will be giving you your carboxylic acid like that. So I hope the mechanism is quite understandable to you all. Proceeding further to the evidences of this particular, okay, this is not the slide related to your acidic hydrolysis. Okay, yeah, so there they have mentioned about the steps of your acid hydrolysis, whatever the steps have been involved, that I've already discussed in the previous slide. And if you want me to discuss that, let's just talk about it again. See what is happening in the first step. It involves the nucleophilic attack of hydroxide ion on the ester carboxyl, forming your tetrahedral intermediate first. That is, okay, let me show you which one is this. This one it is. Yeah. This is your first structure, that is your tetrahedral intermediate, this one. Okay, now after the formation of tetrahedral intermediate, what is occurring after repeated protonation or deprotonation? You will get your required product, that is your carboxylate anion and your alcohol. Okay, so that is all about the mechanism of your acidic hydrolysis. Right, now let's just talk about the evidences in the support of this particular mechanism. These are the two evidences. First one is your site of cleavage and second one is the solvent exchange. In first evidence, you can see what is exactly happening. See, isotopic tracer studies has already confirmed that, like that in alkaline hydrolysis, that a cleavage is occurring between oxygen and the acyl carbon. Okay, and for example, they have also given the similar example related to your alkaline hydrolysis only, so that you can see this by your own. Alright, and if you have, I repeat, if you have not checked out the mechanism of alkaline hydrolysis, the video that I have uploaded just before uploading this video, the link is mentioned in the description box. Just check that first. Okay, then only you will be able to understand the further part. Alright, then second evidence is your solvent exchange. where what is happening, the formation of your tetrahedral intermediate in acidic hydrolysis has been confirmed by O18 exchange between carbonyl, oxygen and solvent. This is also quite similar to that we have discussed already in your alkaline hydrolysis. So next one is your transesterification reaction, or you can also call it as alcoholysis reaction. Okay, so exactly what is happening when this ester is treated with another alcohol like that, in the presence of an acid H2SO4 or HCl, or a base that is R-ONA as a catalyst, it will be giving you another ester, and this reaction involves the replacement of alkoxy part of ester, that is this part of ester, by alkoxy part of alcohol via this part of alcohol taken in excess. Okay, so this particular reaction is transesterification reaction. So example that is they have already shown over here is, you can see the reaction of your distyl tripalmitate with your ethyl alcohol, that is excess of ethyl alcohol has been used over here. So what is happening, this part will be replacing your alkoxy alkoxy part will be of your ester will be replaced by alkoxy part of alcohol. So you can see it leads to the formation of your glycerol and ethyl palmitate. Okay, so that is one thing happening in this case. So I hope transesterification is also quite clear to you all. So you can see, since transesterification it is an equilibrium reaction, the cheaper alcohol must be used in large excess so as to shift the equilibrium more towards your forward side, that is toward your right side. Okay, so the reaction is particularly used for preparing esters of long chain fatty acid present in oils and fat. So this mechanism of transesterification is quite similar to that of base and acid catalyzed hydrolysis of esters described in the previous slides. So talking about ammonolysis, over here you can convert your ester into amides. Okay, so you can see what is happening. Ester can be reacting with ammonia, leads to the formation of RCONH2, and the example has also been given where your ethyl acetate is reacting with ammonia, giving you acetamide and ethyl alcohol. So this is how you can convert ester with your ester to amide by reacting with ammonia, primary and secondary amines to form amides. Okay, so there are also some other reactions that includes reduction. That includes this reduction with Grignard reagent, reaction with hydrazine and hydroxylamine, and Claisen's condensation. So we'll be taking up all these in detail step by step. Let's proceed to the next slide. And yes, in reduction also you are going to see two kind of reduction. That is your catalytic reduction, and okay, let me just erase it first. Okay, then you are going to see over here two kind of reduction, that includes catalytic reduction and your, okay, let me just change the highlight color also. Okay, catalytic reduction and chemical reduction or reaction that you are going to discuss over here. So first of all, talking about your catalytic reduction, what is happening exactly? Your esters can be reduced either catalytically or by a chemical reaction, and each molecule of ester yield two molecules of same alcohol or one molecule of each of the two different alcohol, one derived from acyl part, other from your alkoxy part. So first one is your hydrogenolysis, that is your catalytic reduction, where our ester is reacting with your H2 molecule in the presence of copper oxide and CuCr2O4, and it will be giving you your alcohol RCH2OH or this one alcohol. Okay, so either the two molecules of same alcohol or one molecule of two different alcohol, or one derived from acyl part, one from your alkoxy part. Okay, so that is what the product that you are going to get in this particular case. Second one is your chemical reduction. Okay, so exactly what is happening, you can see your ester is reacting with LiAlH4, that is lithium aluminum hydride, to give again the same product to you, but only the difference is lying in the case of your catalyst over here. Okay, so that is another thing over here. Proceeding to the mechanism of Bovalent blank reduction. Okay, let me just explain. So the chemical reaction that we have seen in the previous slide is nothing but the Bovalent blank reduction only, and we are just going to see its mechanism, how this actually occurs. Okay, see, this is your ester over here, where your R1 is different from R2, and the sodium will be giving the electron to this oxygen atom, and there is occurring homolytic cleavage that you can see, like arrow like this have been shown over here. So after homolytic cleavage and after the donation of electron from the sodium metal, the structure that we have obtained is this one. Okay, and now what is happening? Now your after homolytic cleavage, now this carbon is carrying radical over here. Let me change the color of the pen first. Okay, this carbon over here is carrying radical, and this oxygen is carrying negative charge, and sodium is carrying now positive charge, because sodium metal has donated its electron, so now it is carrying positive charge. Okay, then in the presence of the alcohol R3OH, what is occurring exactly? This oxygen will be getting protonated, or you can say it result into the formation of your alcohol like this. Now this carbon is still carrying your radical. So on sodium, what your sodium will be doing, it will be giving again electron to this particular bond, and now this carbon will be carrying a negative charge over here. Now in the next step, your alcohol again is introduced, that is R3OH, and it will result into the structure like this. So this particular bond will be accepting the hydrogen from this alcohol. This carbon carrying negative charge will be accepting hydrogen from this alcohol, and it leads to the formation of your alkoxide anion like this, that is R3O negative, and we will get this particular structure. Now from this particular structure, what is happening? There is occurring proton transfer and releasing of your R2OH. Okay, so the alcohol that has been released over here is your R2OH, and also in the same step over here is occurring protonation. Okay, not protonation, sorry, proton transfer is occurring, which leads to the formation of your this aldehyde. Now the step that we have discussed from the start is going to repeat again. From this particular step, there is going to occur homolytic cleavage. Sodium metal will be giving its electron to this oxygen bond, resulting in the structure like this, as similar to this particular structure. And there will be introduction of R3OH, which leads to this particular structure, and it will in the end will be giving you RCH2OH. Okay, so that is how the mechanism of Bovalent blank reduction occurs. So this is the LiAlH4 reduction mechanism, where your esters are reduced to primary alcohol. It is similar that we have discussed in the previous slide. What is exactly happening? Oxygen will attract the shared pair of electron towards itself, and this carbon will be accepting hydride ion from this particular LiAlH4, and then what is next is your alkoxide ion will be released from here, and it result into the formation of this aldehyde, which again after getting after accepting hydride from here, hydride ion will be attacking this particular carbon, electrophilic carbon, what it will result into the formation of this particular primary alcohol after hydrolysis. Okay, so that is similar mechanism, quite similar to the previous one. So next reaction is with the Grignard reagent. Over here you can see the reaction of your ester with RNGX in the presence of dry ether. It leads to the formation of first unstable product like this, where your oxygen will be attracting shared pair of electron towards itself, making carbon susceptible to get attacked by your R negative, that is particularly RMGX. Okay, not RMGX, actually R. It is going to get attacked by your nucleophile. Okay, then after getting attacked, you will be getting this particular addition product, which is quite unstable, and from here you can remove your MgOCH2H5X, which will result into the formation of aldehyde, which in this particular case further reaction with your Grignard reagent leads to the formation of secondary alcohol. So you should remember, with the reaction with LiAlH4 or Na or alcohol, what happens is your reduction of your esters to primary alcohol, and over here you can see the reduction of your ester to secondary alcohol with Grignard reagent. So there are some other examples that you can see by yourself, the similar examples related to the mechanism that we have discussed in the previous slide. Okay, so proceeding to the third reaction, that is reaction with hydrazine and hydroxylamine, where your ester is reacting with hydrazine and it leads to the formation of acid hydrazide like this, and alcohol is removed. Okay, so exactly this is happening, and after and the reaction of ester with NH2OH, it releases your hydroxamic acid and alcohol. Okay, so hydroxamic acid is forming purple red complexes with ferric salt. Therefore, this reaction is actually a test for esters, and this test is your hydroxylamine amine test, acid test. Okay, hydroxylamine acid test. So over here you can see after reaction of your ester with hydrazine, it leads to the formation of acid hydrazide, and reaction with NH2OH, it leads to the formation of hydroxamic acid. Okay, so proceeding further to the last reaction, that is Claisen condensation. What is happening actually, the ester is having alpha hydrogen is is actually undergoing self condensation in the process of a strong base, such as in the process where strong base is being used, such as sodium alkoxide, and it leads to the formation of your beta keto ester. So you can see your ester with alpha hydrogens having two molecules, it leads to the formation of removal of this R-OH and beta keto ester is formed. Okay, so in the mechanism you can see what is happening. Reaction of your sodium alkoxide with ethyl acetate leads to the formation of this particular nucleophile, which will be reacting with ethyl acetate to give this particular structure, and after removal of this OC2H5 negative, it will be giving you your ethyl acetoacetate. So that is all about this particular chapter, and here I am stopping my video. So I hope this is quite understandable to all of you, and if there is any query you can mention in the comment box. So yeah, thank you so much for watching. Do subscribe my channel and press the bell icon for more updates.